இப்போ வாய்ஸ் இங்க பாரு வெளியே வந்துருச்சுப்பா. இல்ல இல்ல கேக்குதா கேக்குதா? ஓகே ஓகே ஓகேப்பா ஓகேப்பா. ஓகே. Converter with so
Sir,
in the converter may so but now my voice is audible. Okay, okay, okay. Yeah. So the DC to DC converter is nothing but of AC transformer. So we know the transformer means either we can step up the voltage or step down the voltage. So likewise, DC to DC converter means either we are going to increase the input voltage or we are going to decrease the input voltage. If we are using into the buck converter means we are going to step down the DC voltage, but we are going to increase the voltage means we need the boost converter. But today we are going to discuss about the buck converter design. Okay, so this is the buck converter circuit diagram. So we have a one RLC. So the resistive load I am taking into the resistive load, and one switch is there. Either we can use the MOSFET or IGBT or SCR. You can use any one of the switch. Okay. So I am going to derive the transfer function of this buck converter. Okay. So once I am going to derive the transfer function means I need a state space analysis model. Okay. So previous series, so we have discussed into the state space analysis model. I think Anbaras and Saris taken this part. Okay, I am going to take the result only. So in state space model we have a state equation and output equation. So the state equation derived from the AX plus BU, that is A matrix plus B matrix. X will be indicate that the state variable, so U will be indicate that the input variable. Okay, so I am going to consider the buck converter. So in this buck converter we have a two mode of operation. One is whether the switch will be on, and another mode of operation is the switch will be off. Okay, so once the switch MOSFET switch will be on means automatically the current will be flows through the the current will be flows through the inductor only. Okay, so the diode automatically comes into the reverse bias. So this diode is during the switch on period, the diode is inactive. The equivalent circuit is drawn in here. Okay, so we have a input source series with the inductor and capacitor. So we are connecting into the R load. First we are going to derive the state equations. So the state equation will be derived with the help of the KVL and KCL. Okay, so wherever we are writing into the inductance equation, so voltage across the inductance means at the time we can use the KVL. So wherever we are going to derive the current through the capacitor, so that place we can use the KVL. Okay, so to see, first we are applying into the KVL. I am going to find the voltage across of inductor, that is nothing but of VL. Voltage across the inductor is nothing but of VL. Okay, so I am going to find the voltage across of inductor. That's why I am going to use the KVL. So here we have a input, we are applying into the loop means, okay, as per the KVL, V in is equal to, so we have studied into the, as per the KVL, input voltage is equal to voltage drop across the element. So V in is equal to VL plus VC. So we need the voltage across of inductor. So that's why we are rearranging into this equation. Okay. So VL is equal to, VL is equal to V in minus VC. V in minus VC. V in minus Vc. Okay. So I am rearranging into the this equation. So we get the voltage across of inductor is equal to input voltage minus voltage across of the capacitor. Here the capacitor and the resistance both are connected into the parallel manner. So the output voltage is, voltage across the resistor is equivalent to the voltage across of capacitor. So we know the in parallel circuit voltage will be same. Okay. So from this we are taking into the next, I am going to find the current through the capacitor. So I am using into the KCL to see current through the capacitor, that is IC, current through the capacitor. So this current through the capacitor is total current, inductor current IL is dividing into the two path, IC as well as IL, nothing but of IR, load current. Okay. So we are writing into the equation means, so the current through the resistance is, I am going to write the in form of voltage. So I is equal to V by R. So current through the resistor IR is equal to P by R, V out divided by R. The V out is nothing but equivalent to voltage across the capacitor. So this is the current through the, this part is current through the capacitor and IL is current flowing through the inductor. So now from these two equation we are going to write the state matrix. Okay. So here we have a two, each equation we have a one differential term. So I di divided by dl and dvc divided by dt. So we are taking into, this is for left hand side, so remaining terms we are taking into the right hand side. So here our state variable is, from the two equation our state variable is IL and VC. So these two are our state variable. So we know the general equation is AX. So this AX is the state matrix. Okay. So X is state variable IL and VC. So plus B matrix. So B is P into U. So U is input. Here we, in these two equation we have a only on input is V in is there. So in first equation, so that's why I am writing into the 1 by L. So second equation we don't know have any input terms. So I am putting into this 0. Okay. So 1 by L 0 into Vn. So in output equation, so V out is, so this is for C into X. C into X. So the X will be indicate that the state variable, that is IL and VC. So C is the output. Okay. So you can compare into these two equation. So here only we have a output term. So VC. So that's why I am writing into the first term. We don't know have any output equation, output. That's why I am putting into the 0. And second term we have one output equation, that is I am putting into the 1. So this is for state matrix. Okay. So during the switch on period. So I am taking into, this is for A1 X plus plus BU. So during the switch on period means I am taking into the A1X plus B1Y. My anybody having any doubt to write the to form the stat matrix? Okay. So next we move on to the switch off period. Okay. To see. So now the MOSFET will be off means MOSFET will be off means okay. The supply is not connected into the load. Okay. So only during the switch on period the inductor will be charged into the up to V in. So this charged voltage going to discharge the switch off period. Okay. So we are draw the waveform means during switch on period the inductor will be charged. During the switch off period the inductor will be discharged. Okay. So this is for D. So D means during the switch on period. 1 minus D means so during the switch off period. Okay. Now the switch off period also, so we have a inductor and capacitor both are parallel. So L into di by dt minus Vc is equal to 0. Okay. So I am applying into the KVL. Next I am going to find the current through the capacitor. So for current through the capacitor I am going to apply the KCL. Here also we have a incoming current for this node is IL is the incoming current and outgoing current is IC and IR, that is nothing but of load current. Again we are rearranging into these equation means okay, we get the IL minus VC divided by VR. So the VC divided by VR is nothing but of IR current. So I am writing into the in voltage term. So that's why I am writing into the VC divided by R into the C into dV. This term is current through the capacitor term. Now we are taking into these two equation. I am arranging into the matrix form means okay. This is for A2 into X plus. So in these two equation we do not have any input term, that is nothing but a V in term. So I am putting into the 0 0. Okay. Up B2 into U. So we do not have any input. Okay. Similarly, in second equation we have a output term VC. So that's why we are writing into the C2 matrix is 0 1 plus D value also 0. D2 into 0. So after we are forming into D2 into U. So after we are forming into these two equation, I am going to find the transfer function. So I am going to find the transfer function. I am going to use the MATLAB. I am writing into the program. Now I am switch over into the MATLAB. If we, the MATLAB is visible இருக்கா? Okay. Yeah. To see. So first I am representing, I am declare into the what are the variable I am going to use. The Vs is input voltage. I am going to use the one inductor, that is L. I am going to use the one capacitor, that is C. So the duty ratio is D and R is resistor value. So I am taking into the of Laplace transform of output divided by Laplace transform of input. Okay. So we need the S domain. For that purpose I am using into the small s. Okay. Next line will be indicate that the state variable. So we are using into the two state variable. So IC and VC. So IC into VL. So I am taking into the I1 and V1. Okay. To see. So from the previous explanation, so we are forming into the A1 matrix during the switch on period. So 0 minus 1 by L, 1 by C minus 1 by RC. In B1 matrix is 1 by L and 0. So if you have a Any doubt means you can refer the this one to see 0 minus 1 by L, 1 by C minus 1 by RC. This is for A1 matrix. In B1 matrix, 1 by L, 0. Okay. So that value will be feeded into the A1 and B1 value. So similarly, during the switch off period also, we are derived into the A2 and B2, C2 values. So these values are, I am feeding into the stat matrix value will be feeded into here. So now I am going to combine these two modes. So already I have set into so the diode already I have set into so during the switch on period, the inductor will be charging, and during the switch off period, the inductor will be discharging. So we have two modes. So this is one mode, and this is the another mode. What I am going to do means I am going to take the average of these two. I am going to take the average of these two. So for that purpose, I am going to take the A1 value as well as A2 value. So I am going to take the average of A1 and A2. A1 and A2. A1 and to see. So the A will be indicate that I am going to multiply the A1 into D. The D will be indicate that during switch on period we have a duty cycle, and A2 will be indicate that the switch off period, that time we don't know have any duty cycle. So that value will be taken into 1 minus D. So this is for this line will be indicate that we are going to take the average of both switch on and switch off period. So the next four lines will be indicate that the average value, taken value. Next I am going to find the transfer function. Okay. So how I am going to find the transfer function means, so we know the value transfer function value is transfer function value is x star is equal to, I am writing into the first equation. So variable is equal to ax. Now, so a1, a2 combined into a, and b1, b2 will be combined into b. So how we are combining means with the help of the averaging. Okay. Now to see, so this state variable will be 0 means, so ax plus bu, ax plus bu. So now I am rearranging the A inverse of minus A inverse of A inverse of B B into U. So now I am finding into the transfer function means S is the variable. So U is the input value. So X by U is equal to minus A inverse into B. A inverse into B. So this is the transfer function. So I am going to find the two transfer function. Why I am taking into the two transfer function means, so from the circuit diagram we have a two inputs, one for V1. Either I am going to change the input voltage, or otherwise I am going to change the PWM signal. So that is nothing but of D. So for that purpose, I am going to find the two transfer function. Okay. So input is varied means what is the response of output? That is the one case. Another case is I am going to vary the duty cycle. PWM means So what is the output? So if I am varying into any one quantity means one of the quantity will be constant. I am varying into the V in is varying means D will be constant or otherwise vice versa. So for that the U is general form. Okay, either I am going to change the input voltage or I am going to change the duty cycle. So for that case, next I am going to write this line in MATLAB. See, so X is equal to minus A inverse into B into VS. So now the VS is nothing but input voltage. I am changing into this means. So we get the transfer function of output versus input. Okay. So and another one transfer function is nothing but of output versus duty cycle. The duty cycle will be denoted into the BD. So the I am using into A1 minus A2 into X. This is the formula to find the output versus duty cycle transfer function. Find particular formula. Okay. So I am adding into these two. Okay. So now I am simplifying into to see these two lines are very important one. Okay, so these two lines will be decided into the transfer function value. Okay, so now I am running into this program means and this is the one more transfer function to see. So V underscore V1, that is nothing but of output versus input voltage. Transfer function is this one. So next line will be underscore D will be indicate that the output versus duty cycle transfer function. Now you can look into the this transfer function. I am considering only for the output versus duty cycle transfer function. I am going to keep the input voltage is constant. Okay, so we get the R into Vs divided by CL or S squared plus LS plus R. Now in denominator term we have a R is I am going to take down the R is outside. So the numerator denominator R will be cancelled. So we get the LC S squared plus L by R S plus 1. That is nothing but of this is for series RLC standard formula. We get the series RLC standard transfer function. Okay. Ma, anybody having any doubt how to find the transfer function அப்படிங்கறதுல எதுவும் doubt இருக்கா? Okay. I okay, so now I am going to design the buck converter. So in I am going to take the output. I need the output is 15 volt. So I am giving into the output input voltage is 48 volt. I am taking into the load resistance is 8 ohm. The switching frequency is 40 hertz. Okay, so for this case first I am finding into the duty cycle. I am finding into the duty cycle. So we know the formula for buck converter duty cycle. D is equal to V out divided by V in. That is nothing but of Vs is nothing but of input voltage. So 15 divided by 48, we get the 31.25 percentage of duty cycle. Next, I am finding into the inductance value. So L is equal to 1 minus, this is the formula. So this formula is available in all the standard textbook. Okay, so we get the inductance value. Okay, but I am taking into the assuming into the inductance is 25 percentage larger of inductor current. So that's why I am taking into the calculated inductance value is So 25 percentage. So finally we get the 85.93 microhenry. Similarly, I am finding into the capacitance value. So this is the formula. So this term is nothing but of, so we are assuming into the, we need the 0 percentage of tolerance, but in it is practically possible. So that's why I am taking into the ripple factor is, I am taking into the 5 percentage. So this ratio is 5. I am considering into the 5 percentage. So from this 5 percentage, I am calculating into the C value. So C value is equal to 125.01 microfarad. So for my design, I am calculated into the duty ratio L and C value. So I am going to simulate this value with the help of the MATLAB Simulink to see. So I am take the element from library. After that, I am connecting into the all the element to see this is the my pulse. To see, I am giving into the switching frequency is 40 kilohertz. We need the time period, so I am taking into the reciprocal of frequency. So we calculated into the duty ratio is 31.25 percentage. So after that, we are choosing into the, my input is 48 volt. I am applying into the 48 volt. So L and C value will be whatever I have calculated. So that value will be applied here to see 125 microfarad. So my load resistance is 8 volt. So now I am simulated into this one means to see. So we have designed into the 15 voltage. We need the output is 15 volt, but in open loop condition, we didn't reach the exact 15 volt. We have a some deviation is there. To see, we are not reaching into the 15 volt. We are reaching into the 14 point something voltage, but we get the uh, perfect waveform. We don't know have any maximum peak overshoot, okay, but we will achieve the settling time is nearly is equal to 0.06 second. 0.06 second only we are finding into, we are achieving into the settling time. So from this we can calculate the rise time, peak time. So whatever may be our time domain specification values will be calculated from this graph. Okay. So the same waveform I am going to obtain the with I am going to obtain the with transfer function to see. So next to see. So this is the transfer function block. So before that, I am not going to introduce the controller. Okay, I am going to introduce the open loop, same pulse only. I am going to see. Already we have calculated into the transfer function is Vs divided by LC S squared plus L by R S plus 1. Okay. So now I am calculated into the RLC value. So I have applied into the this RLC value. I got the second order equation, in numerical form. Again, once again, I am going to simulate this one. In first diagram will be shows the I am simulated with the help of the components. For second diagram shows the simulation with the calculated transfer function. Now you can see, so we have a difference between first output and the second output. In first output we don't know have a any maximum peak overshoot. Okay, so but in this case we have a peak overshoot is there. We have a peak overshoot, but we are achieving into the less steady state time. So in previous graph we have achieved into the steady state value is 0.06 second, but in this case, so with the help of the transfer function we have achieved into the steady state value is before the 0.02 second. So the settling time will be we have reduced, but in this graph we have a some maximum peak overshoot is there. Okay, and rising time, peak time will be differ from the previous case. We are going to design the perfect controller. We are going to reduce the these maximum peak overshoot everything. So here the maximum peak overshoot is, you can look into the nearly we have a 27.5 is there. To see, before applying into the controller we have a 27.5 is there. So now I am going to apply the controller. I am going to apply the PID controller. Okay, anybody having any doubt up to this? So how we can obtain the transfer function? So how to obtain the response of transfer function அப்படிங்கிற anybody having any doubt?
No, sir.
For second year students, now in this semester you are studying into the control system. Okay, in that paper you are taking into the this numerical value randomly, you are choosing into this numerical value. Okay, so you are analyzing into the time domain specification everything, but the purpose is whatever may be this numerical value, that value will be derived from the design only. Okay, if you are going for the higher semester, you are studying into the power electronics, or otherwise you are doing into the any project, any power electronics related project. Once you derive the mathematical equation means, easily we can achieve the time domain response values is decided time domain response value. How we are achieving into the time domain response value means, so we know the standard value is s squared plus 2 theta omega n plus omega n squared. So the theta will be nothing but of damping ratio value. So easily we can adjust into that damping ratio value. We can achieve into the either under damped or over damped or natural damped value will be easily achieved, but that will be not achieved with the help of the this first circuit. So we can randomly changing into the capacitance inductance value, that is very tedious process. Okay, so once we can find the transfer function means, so we can change only for the that zeta value alone, so we get the perfect output. Now I am going to introduce the controller. Okay, so I am going to introduce the PID controller. So now we are up to this, we are discussed only for the open loop system. Now I am going to introduce the controller that is comes under the closed loop. So initially you can take the, either you are going to apply the PI controller or PID controller or P controller or I controller, whatever may be. So you can first you can set the initial value is 1 1. Now we know the closed loop system means we are comparing to the output voltage into reference voltage. Here I am taking into the my set point or reference point is 15 volt. So why I am taking into the 15 volt means we need the output is we are designing into the buck converter for output voltage is 15. So that's why I am taking into the reference point is reference value is 15. So this is the 15. So I am comparing into the output into input. If error will be occur, automatically error will be occur. To see previous case we get the 14.98. So 15 minus, so we get the some error. The error will be given into the PID controller. Okay. So once you can set the PID block means you can apply the initial value is 1 1. So P value 1, I value 1. So you can, after applying this, I am going to tune the PI value. So after that you can press the tune value. So that will be get the linearized plot. So so this is for non-linearized circuit. I am going to linearize the this non-linear into linear circuit. To see, we can saw the open loop system. So open loop system will be get into like this. So I am going to take the new system. I need no need of this oscillation. Okay, we need the smooth one. So for that purpose I am taking into the new one. So already we have simulated. I am getting into that simulated value. Give the step input. I either impulse. So I am going to take the step input. So the step value is I am going to choose the not for 1. So I am going to take the 0.3. You can give the duty ratio value. After that you can run the simulation. So it will take some time. So apply and close. To see, so the green color waveform will be indicate that the actual output value. The blue color will be indicate that the modified one. So you can change this one is so how you want to response means you can change the that blue color line. So I need the less settling time. So I am changing into this one. So here I am going to obtain the underdamped. So either you can use the one pole. This is for compensation technique. You can add the one pole or you two real pole. So I am going to take the underdamped pair. Underdamped pair means we get the so complex value, complex conjugate value. Okay. So I am going to estimate the that value. So how many samples are taken means I am taking into the 51 samples. So these things automatically calculated. Okay, no need worry about this. So after that we can apply. to see. Now we get the p and I value. So p value is 0.04427. We can apply the here. So p value is, so initially we can take in into the 1, but 0.4772, and I value is 17.77, I think 17.77, 0.04427, 4427. Okay, you can, so after tuning you can apply this value. So now I am tuned into the my PI controller. So after that I am going to run the simulation to see. So before introducing into the PI controller, so the output voltage is we get the 14 point something, I think 14.98. Now you can look into this, means we get the exact 15 volt. So we need the 15 volt output. The 15 volt output will be got it here. So I am going to check the my reference to see now. So before applying into the controller, my peak overshoot is nearly 27.5. Now the peak overshoot will be reduced into 20, but still now we have a response. Okay, we have a some transient is there, and also we are achieving into the settling time is very less. So before that we are achieving into the 0.02, less than 0.02. Now itself we are achieving into the settling time is less than 0.02. So now after tuning I am reducing into the maximum peak overshoot from 27.5 into 20. So this is I am achieving only with the help of the simulink only. Suppose I am going to derive the PI value in mathematically means. So after deriving into the PI value in mathematically, so whatever I am calculating into that value will be applied into here, means we get the exact output value. So we will easily reduce the maximum peak overshoot, and apart from this we will achieve possible with the help of the transfer function. So here we have only one parameter is that zeta value. So you have studied into your in your second unit, control system second unit, time domain specification. So that zeta value will be decided into the underdamped or overdamped or natural damped. So that value will be changed, means we get the our decided output value. So this is for time domain specification. So this is for time domain. I am explaining into the time domain specification. Suppose we want to go for frequency domain, means it is possible. Okay, so frequency domain will be obtained with the help of the Bode plot, polar plot, like that. Okay, so that is also possible. So that will be possible for only we can calculate it into the transfer function. Without transfer function we can't obtain, we can't analyze the frequency domain. So டைரக்டா வந்து இந்த எலமெண்ட்டை வச்சுக்கிட்டு நம்மளால frequency domain பண்ணவே முடியாது. அப்போ frequency domain வேணும் அப்படின்னா we need the transfer function. Okay, anybody having any doubt up to this?
No, sir.
Next we go for the frequency domain. So we have a transfer function value. So again you can open the new window, you can apply the numerator value. So we have calculated into the numerator value is to see 48 and the denominator value is, so everything you have did the your control system lab. So you once you can got the numerator and denominator easily, we can put the body plot with the help of the MATLAB to see. So 1.0744, 1.0744 s power 7 4 power minus 8 s square term and 1.074 exponential minus 5. This is for s term and constant term is 1. Next, body of numerator comma denominator. To see, now we got the body plot. So you can decide the gain margin and pace margin, whether the system is, so our title is stability analysis. Okay, whether the system will be stable or not அப்படின்னு check பண்ணணும். To see, I am checking into the stability. Yes, so my system is stable. So whether closed loop system is stable, yes, the system will be stable. So I have obtained into the pace margin is 0.866 and gain margin is 2.24 e to the power minus 7. So for buck converter is, we got the second order equation. So the second order equation in denominator, all the terms are positive values. So once you can check the, so from problem itself whether the system will be stable or not அப்படின்னு check பண்ணணும். அப்படின்னா the denominator value all are positive value means the system will be stable. If any one of the value in denominator will be negative means the system will be unstable. So whatever may be the problem, from problem itself we can say that the whether the system will be stable or not அப்படின்னு சொல்லி conclude பண்ணிடலாம். So here we are derived into the buck converter transfer function. The transfer function itself, the denominator terms are all are positive. So automatically the system will be stable system only. Okay. Thank you. If you have any doubt is there, please ask. My anybody having any doubt?
Sir, very good evening, sir. Myself, Ovi Varshini.
Yeah. OV, yes, ma.
I have a doubt, sir.
Yes.
Can you tell us about microconverters which are used for power applications?
Yeah. Microconverters.
which are
Ma,
used
once
for
again repeat.
yes,
Yeah,
microconverters, which are used for power applications.
yeah. For example, we are controlling into the speed of the motor means, so in your laboratory, regular laboratory, we are doing into the some speed control methods are there. You are adjusting into the rheostat, or we are applying into the brake drum, any something is there. But once we go for the power electronic devices means, okay, we can change the duty cycle itself. Once we can change the duty cycle means, automatically the pulse width will be varied, so the pulse width will be control the speed of the motor.
Yes, sir. Thank you, sir.
Thank you.
So we have certain questions from the participants in the chat box.
Yes
First
ma'am.
question
Yeah.
is from Ashwin D. What are the basic
uh,
requirements to do stability analysis of buck converters, sir?
ah that's why I am saying into my presentation itself. So we are designing into the buck converter, okay, with the help of the simulink. So we are directly applying into the inductor, capacitor, everything means, so we can't obtain the stability value. How we can obtain the stability value means, we can change the element values. Either we can change the inductor value, either we can change the capacitance value. So that is very tedious. So that will be done by with the help of the trial and error method. But we can find the transfer function means, we can find the transfer function means, so easily we can obtain the stable system. So how we can obtain the stable system means, with the help of the that value, that is nothing but of zeta value. So we know the second order equation value is, so s squared plus 2 zeta omega n plus omega n squared value, that is standard value. So we can easily adjust the that zeta value. We can obtain the our record system response, either under damped system or over damped whatever we want, we can easily obtain into that system response. That's why the beauty of the transfer function.
Yes, sir. Thank you, sir. The next question is from Harini Gopal. What are the ways
Yeah.
to improve the overall efficiency of buck converters, sir?
So we are improving into the efficiency means, so we are, so initial we are using into the capacitance and inductance value. So both are storing element value. So in initial, in due to aging condition, these elements are, okay, due to aging, these elements are, the storing capacity will be reduced. So we can't achieve into the our desired efficiency. Okay, so we can obtain the overall efficiency means, okay, so we can frequently for analysis purpose, we can take into the transfer function is good. But we can apply into the practical case means, okay, so we need the good efficiency means, frequently means we can checking into the our component. So many parameters are there. So we can take the, we can measure the capacitor voltage, capacitor current, inductance voltage, inductance current. So everything will be perfect means, we can obtain the good efficiency, or otherwise we can lose the some efficiency more.
Yes, sir. Thank you, sir. I hope that's the end of the query session. Thank you for answering the question, sir. It was really an informative session for us. Now, I would like to
Okay.
call to distribute a gesture of appreciation to our resource person for the day, Mr. Jeyaprakash N. Sir, kindly accept the e-memento as a token of gratitude, sir.
Thank you, ma. Thank you.
Yes, sir. And sir, with your permission, can we have a group picture?
Yeah, yeah.
Yes, sir. I request all the participants to turn on the camera.
Okay, thank you, Pa.
Thank you, sir, for
So if you have
capturing.
any doubt regarding control system, so anytime you can approach. So whatever may be the doubts, so not only for the subject. So for practical example, you can need the any like this. So derive the transfer function for very complex circuit. You can approach us.
Yes, sir. As we
Okay,
bring
thank
this
you, Ma.
session to a close, let's proceed with a vote of thanks. On behalf of the entire Insegnante team and our student members, I want to express a heartfelt appreciation for your enlightening presentation on stability analysis of buck converter using MATLAB. Your insights into leveraging IEEE resources to empower student members in their career pursuits were truly invaluable. Your expertise and passion have undoubtedly inspired us and provide a clean roadmap for navigating the path to success within the IEEE community and beyond. Thank you, Mr. Jeyaprakash sir, for your dedication to nurturing the next generation of leaders and for sharing your knowledge with us today. Your presentation has left a lasting impact, and we look forward to applying the knowledge and insights gained to drive positive change in our endeavors. Thanks for volunteers. Volunteers do not necessarily have the time, they just have the heart. We would like to express a heartfelt thanks to the volunteers who decided their time and effort to make our event a resounding success. Their hard work and commitment have been invaluable. We are pleased to introduce our dedicated volunteers, poster and e-memento done by Hari Prasad, hosting content done by Hari Prasad, feedback link created by Sanjana. Hosting was done by myself and Malini. Each of them has played a crucial role in ensuring that our event runs smoothly and leaves a lasting impact. We also want to thank our HOD, our SB advisor, Dr. Jairama Pradeep ma'am, and SB counselor, Mr. Srikant sir, for their support. Thank you once again to our wonderful team of volunteers. Let's end this session with the participants' feedback. Participants' feedback makes our forthcoming sessions more valuable. Now, the feedback link will be posted in the chat box. Participants are kindly requested to fill out the feedback form before leaving the session to receive your e-certificates. Thank you all. Participants are kindly requested to fill out the feedback form before leaving the session to receive your e-certificates.